limits and continuity go hand in hand. So when we talked about continuity before in pre-calculus, we were talking about, what are some of those domain restrictions, right? So where can I keep drawing and never have to lift my pencil? Or where are places where I'm going to have a hole or an asymptote? Oh man, I bet you were wishing you wouldn't hear those words again, but we are. We're going to talk about holes and asymptotes. So dig out those foldables we had from last year about holes and asymptotes and remember what continuity means. So these are places a function is continuous if I could just draw it without lifting my pencil. That's how we've always defined it. But guess what? In calculus, we have a new definition of continuity. In fact, this is a definition that is so important that I want you to write it down. I want you to circle it. I want you to mark it. I want you to know this definition backwards and forwards because there's going to be times in calculus where you're going to have to recall and prove that a function is continuous because some of the things that we do, some of the theorems that we use, we say this function has to be continuous on the interval 1 to 5 or whatever. And you have to be able to prove that it's continuous. And you can't just say, well, it seems continuous or there's no domain restrictions. You have to know 100% that it's continuous. And how do we know that 100% that something is continuous? Well, if a function is continuous where its limit and function values are the same. So the idea is a function is continuous at C if and only if the limit as x approaches C from the left of f of x equals the limit as x approaches C from the right. This is just not wanting to write for me today, of f of x. And it also equals f of c. Okay, so in other words, this is like that graph that we looked at before. Up here, we look at this graph. The function is continuous here because the limit from the left is 1, the limit from the right is 1, and the function value is 1. Therefore, this is continuous right here. It is not continuous right here because the limit from the left is 4, the limit from the right is 4, but the function value itself is 1, okay? So the definition of continuity is the limit from the left, the limit from the right, and the function value all have to be equal. Therefore, if those are, then they're continuous. Now remember there's different types of discontinuities. There's removable discontinuities and non-removable discontinuities. And the different types of discontinuities are holes, vertical asymptotes, and jumps. Okay, and so we'll talk about those here in a minute. Let's just list all the x values that have discontinuities in the function that we saw above. Okay, so it just says the x values. So where are we discontinuous? Okay, so we are continuous here. Again, we can use like our non-formal proof right now where we can just say like, let's just draw with our pencil and let's figure out where we have to lift up. Oh, we have to lift up right here. So at x equals -1, I'm just going to write it right here so that I don't forget it. Write it right there. It's discontinuous. And then right here at x equals 2, I would also have to lift up my pencil. And then at x equals 3, I would also have to lift up my pencil. And at 5, I would also have to lift up my pencil as well, right? Because I would have to jump. Now, we could go back and we could just define these in terms of our limits. And we could look at this and say, okay, well, the limit from the left and the limit from the right do not equal the function value. Therefore, this one is not. Same here, the limit from the left and the limit from the right. The function value here doesn't even exist. So it can't be continuous if the function value doesn't exist, right? And same thing here. The limit from the left equals -1, but the limit from the right and the function value both equal 2. Since all three of them aren't equal to each other, this isn't continuous. So you could just write those down there. I'm not going to transfer them right now. All right, so remember all discontinuities can be classified as removable or non-removable. Removable discontinuities are holes in the graph, okay? Remember, so it looks like I just like picked up one little point out of the graph, and that if I put that point back in, it would be continuous. So in our graph before, this is a removable discontinuity because if I filled in this hole right here, then I would have a continuous function. This one's not a removable discontinuity because I couldn't just fill in one of the holes and suddenly have a continuous function, right? It jumps. And same here at the asymptote. I can't just fill in like one little spot. It's an asymptote. It keeps going to infinity. So there's really no way to just fill in one little hole, okay? Removable discontinuities are holes. Non-removable are jumps and asymptotes. So now remember, how do we find these algebraically? How do we find discontinuities algebraically? So remember, if I have something like a function and it's factored x minus 2, x plus 1, x minus 2, x plus 3, okay? Now remember that I'm going to have domain restrictions wherever this creates a 0. Sorry, wherever this creates a 0 because I can't divide by 0, right? So I'm going to have domain restrictions. X can't equal 2 and x can't equal negative 3 because if x equals 2, then this whole thing is 0. And if x equals negative 3, this whole thing is 0 and we're dividing by 0 and then we like blow up the world and stuff and we can't do that. So I have domain restrictions or discontinuities at 2 and negative 3. The question is which ones are holes and which ones are asymptotes? Well, if you remember, this one actually cancels out with the top. So I have x equals 2 and x equals negative 3 are my discontinuities. So the ones that cancel out are removable. Those are the holes. And the ones that don't cancel out are asymptotes. Now, you aren't going to see a jump very often in, ever in like a function, like a rational function like this. You're going to see a jump in piecewise functions often. But other ones you aren't going to see the jump. So remember, this one's going to be a hole. And this one's going to be a vertical asymptote, okay? Because this one didn't cancel out. The factor that didn't cancel out, it's 0 is our vertical asymptote, okay? So if you have to go back to that, let's remind ourselves of that, that we can find it with algebra, okay? So which of the discontinuities from example 13 are removable? Oh, we already talked about that. We got this. We don't need to do that. You guys have got this. All right. The main thing I want you to remember is that if they cancel out, they're a hole. And if they don't cancel out, they're a vertical asymptote, because that is something that we see over and over and over again with finding discontinuities. Okay. So when we're doing limits, and we have a continuous limit, or we have a continuous function, we know that that means the limit from the left equals the limit from the right, and it equals the function value, right? We know this, right? Limit from the left equals the limit from the right, and it has to equal the function value. So we can do this thing called direct substitution, which basically means we know what the function value is. We know that we can just plug the value in for the function and find it, right? And so if we can find the function value, we automatically know the limit, because the limit tells us, you know, if it's continuous, we limit from left, limit from right, has to equal the function value. So the easiest thing to do, and this is what we're always going to try first, especially if we know that it's continuous, we're just going to try direct substitution. We're going to plug the value in and see what happens. So for this one, we're just going to plug 3 into this and find out what the function is equal to at 3. So the limit as x approaches 3 of 3 times 3 squared, which is 9, plus 2. So that equals the limit. We're just going to keep copying down the limit so that we remember. Oh, and I was talking, so I can't write and talk apparently at the same time. 3 times 9 is 27, plus 2 is 29. So the limit as x approaches 3 of that function is 29, because the function value is the limit, okay? So let's look at this one. Same thing, direct substitution, we just plug the 1 in. So we get 1 plus 1, and we're actually not going to copy down the limit right here. We're just going to do the direct substitution, and then we're going to define the limit. 1 plus 1 over 1 plus 1. So this is 2 over 2, which equals 1. So the limit, so this is where we're going to copy it down. The limit as x approaches 1 of x squared plus x over x plus 1 equals 1. Okay, because that's the function value, and since this is a continuous function at that point, we can just use the function value.